If you're running AI agents, you're wasting GPU and your agents are getting slower. Not because your model is bad, but because the inferencing stack that you use, namely vLLM, is not agent aware. But thanks to this new recent research called TokenCake, they are proposing a KV cache centric framework for saving LLMs or AI agents, but being agent aware. That means you can now fit much more agents to your GPU, make your inferencing of agents 2 times faster with increased throughput. In this video, I'm going to show you how this works and how you can use it in action. Let's just start with what is the challenge that you're dealing right now with your AI agents, and then see how TokenCake can be a great solution. If you're running your AI agents locally with your own GPU, so that means you're hosting a language model, there's a great chance that you're really wasting GPU and you're not in an optimized manner. Because a lot of open source inferencing frameworks that host language models on GPUs or TPUs, let's say vLLM, which is pretty well known and I think the most popular inferencing framework as of now, is not aware of your agentic use case for KV caching, which is very important for GPU utilization. But what is KV cache? Well, KV stands for key value. When you are actually inferencing a language model, it calculates each token by GPU of the given prompt. Let's say your prompt has 3 sentences. It also needs to calculate the tokens of all previous words and sentences that you have in a given prompt and calculate the dot product between tokens and previous tokens. So that dot product is called value. That shows how much model should focus about the past and past sentences to understand the current token and then the next token. So it's worth to cache them, because if you don't cache it, you need to recalculate token for all the sentence you have given in your prompt, which is not really fair. And of course, a waste of GPU. So vLLM does that in a first come first served manner and save that cache in GPU memory, which is pretty gold, and we have to be cautious about how we utilize that GPU memory. But the challenge is, in your agentic use cases, the solution is not just calling a language model. It's much more complex. To give you the challenge here, when you're actually using AI agents, you're doing function calls. That means your AI agent is calling web search API or calling your documents API, your search index, your RAG. So you have to wait for that tool or MCP server to be finished so your language model receive the context and respond to you. That wait time can cause actually idle times that you are not utilizing that GPU memory efficiently, because potentially you, let's say, save some KV caches and waiting forever for that tool function to be finished, which is not fair, because you could use that GPU memory for doing other stuff instead of just waiting forever. So that space contention is a secondary challenge. Critical agents evicted by non-critical ones, causing expensive recomputation. So what does this one mean? When there is no memory in your GPU because you have KV cache a lot of stuff, then you have to drop some of them to give some extra space for new agents or sub agents that you're calling them for the given query. And that means you have to drop whatever you have cache and you have to recalculate or recompute all that KV values for finishing that multi-agent framework task, which is again not efficient at all. And it introduces latency because your processing is taking more time. And last but not least, because you have a function call in your AI agent, sometimes agents need to wait for seconds, let's say 1 to 30 seconds for an external tool to be finished. And you have just cached that KV for nothing, sitting in the GPU memory and not utilizing that properly, because your whole inferencing system, let's say vLLM, is not aware of what agent is doing what, which sub agent you have called, with what function tool, how much function tool is getting the duration of that to be executed. So with all those blind spots, you are not really fully leveraging GPU memory in a proper way, and you're just slowing down your AI agent. So what TokenCake proposed in the paper, as I was going through that, they're saying that in this new solution, they have a new, let's say, vLLM type of format, which is for inferencing. But this time they're doing KV caching, which vLLM does as well, but making sure it knows your AI agent and is agent centric. It is agent aware and it's not blindly doing just KV caching. And by doing so, they're saying that they sort of speeded up the performance of agents up to 2 times faster, and they increased the GPU utilization up to, let's say, 17%. That means you are wasting GPU 17% less. And obviously, our ideal scenario is when we use GPU utilization 100%, which we are really making the worth out of the money we are paying for the GPU, which in either world 100% is really optimal and maybe far to reach, but even 70% for utilization is a gain by itself. And obviously, because you're making it faster, you have utilized the memory in a better way, so your throughput is also 2 times more, so you can call your AI agent in parallel much more and also serve more people in the same time when you are hosting your AI agent. So let's see how TokenCake does that. They are actually proposing a contribution in 2 approaches. First, they are saying that we are now creating an agent-aware KV cache management by doing 2 things. First, a space scheduler. Second, time scheduler. This is what they're adding to the inferencing. So let's see what is a space scheduler. They're saying that instead of just naively save some partitions of GPU memory for KV cache, I'm going to do that dynamically. So what does dynamic mean? That means I want to understand which agents are more critical, so I save their KV cache in the GPU memory and drop the ones that I can maybe recompute them in a much cheaper way. So I will hold the GPU memory in a way that I'm really choosing the most critical path to be offloaded to the memory. To give you an example of what do they mean by a space scheduler through considering critical agent, they are actually doing so by a hybrid approach. So they consider that what is your end-to-end general architecture of your multi-agent system. They create a DAG out of it. I'm gonna show more details of that later. So they consider that which agent is going to be called by what agents and when, and which one is more important. Then at the same time, when you run your agents for a couple of times based on how they are behaving, how much each one going to take longer, they calculate if your agent is critical or not, and if we should add dedicated GPU memory for the KV cache of that agent necessarily, and how we manage that. So this is for a better, more optimized way of utilizing the space of your GPU memory. But the other side, which is the second contribution they have, is time scheduler. So what does time scheduler here? When we are calculating all this KV cache, and potentially some of them going to be very large, if you have a lot of context, a lot of long prompts, then we have to maybe offload them out of GPU memory and push it to CPU memory that we can have more space and it can be even cheaper. So by doing so, I have to ask myself that when do I need to offload that KV cache from GPU memory to CPU? Is it the right timing? How much of that I should do? Because that transfer gonna cost me. So is it cheaper to transfer to the CPU memory, or it's cheaper to keep it in GPU memory? So they call it proactive offload and predictive upload. So TokenCake by itself will calculate and answer all the questions that I just raised to understand, do I need to offload it to the CPU memory? And after that, when do I need to put it back automatically to GPU to use it? Which vLLM stuff, they don't have these features, and they have it in TokenCake. And I'm going to talk about the details exactly how they know when to upload or offload. All right, let's get to the details of their first contribution, which is a space scheduler, and they're dynamically doing memory partition of GPU for critical agents. Let's deep dive into that. So they're saying that with this space scheduler, we divide GPU memory into 2 pools. First, a shared pool for all the agents, and then a dedicated reserve pool of memory exclusively for critical path agents. Then here's the main question. How does TokenCake know which agents are critical in my design? Well, here's the pseudocode to give you the concept. What they do is that they calculate this reservation algorithm for understand which one is critical based on 2 metrics, static and dynamic. Static is about they will understand your whole end-to-end agentic framework to see with the given agent where that agent is from that DAG and how many other agents or sub-agents or tools are dependent to that given agent. Obviously, that degree is higher. That means that agent is more important and more critical, so we have to dedicate a GPU memory for KV caching of the context of that given agent. Then the second priority measurement is dynamic. That means when you run your agent, this is going to be calculated. So it depends on wait time and the amount of token requests that agent calculate based on given time. So that means when the wait time is more and that agent is calculating much more tokens and do a lot of stuff, obviously it's a more important agent. And then we just multiplying these 2, we have this hybrid priority score. So based on this, we specify top agents ranked by this hybrid priority score. Then at the same time, we don't just dedicate, let's say, 70% for shared pool and 30% reserved for that critical agent. That might be the default, but as we go and use it based on the system pressure and the pressure that we have on GPU memory, we recalculate this portion and percentage. For example, if GPU usage is more than the threshold that you specify, I will adjust the reserve ratio a little bit more to make sure those critical agents still they have their own memory reserved even in high pressure scenarios. So that's another dynamic way of calculating this allocation strategy, and based on this weighted allocation, each critical agent gets much more memory based on the usage history, which is that dynamic part, and priority, which is static. We just understand what's the priority of that agent immediately as I see the DAG of your agentic framework. All right, their second contribution is time scheduler. So they proactively can offload and upload KV cache from GPU to CPU to manage that utilization and also efficiency of inferencing the language model for AI agent. Then how do they do that? In your AI agents, first you do FC, stands for function call. Your agent will call a function. They will decide to see, okay, now the GPU is waiting for nothing because your agent is calling a function call that has nothing to do with GPU. So shall I just drop that KV cache out of GPU to CPU? If yes, okay. And then I will load it back to GPU, but I need to define when. Obviously, when that function call is completed. Then it has to predict when your function call is done. So now your agent is ready for the next step. Now we need to load that KV cache from CPU back to the GPU memory. So how did they do it? First, they calculate one thing. I need to understand if the benefit of scheduling is more than transfer. That means I'm gonna just offload that KV cache from GPU to CPU if the waiting request can complete within the available window. That means if you're calling a web search API as a function tool, and it's gonna takes, let's say, 30 seconds. And if I offload that KV cache from GPU to memory, it's gonna take 10 seconds. So that's okay, I might do it because 10 seconds is less than 30 seconds. But if offloading that to CPU gonna take much longer than your agent calling the function, then it's waste because I cannot finish that transfer between 30 seconds. So I might not transfer it. Not only that, then at the same time, let's say I decided to transfer, then I wanna know how long that function call gonna take in action to make that decision. So how they do it, based on two things. They will ask you, based on your experience or your design, how much that function call will be taken. Let's say web search. You say 20, 30 seconds. That can be just an estimation. So that algorithm use your estimation plus all the historical execution that you have done so far with that function call. They will use it to calculate that final time to get an answer for this equation here. And let's say they're gonna say that it's gonna take 60 milliseconds for transferring this to CPU, but this amount of milliseconds to recalculate that KV cache. So obviously 150 times faster than recomputation, I'm gonna actually transfer it. I'm not going to make 150 times fake time to just recalculating that KV cache, which is absolutely valuable for me. So what they did in the paper, they started to benchmark themselves with much more popular inferencing frameworks, namely vLLM, Light LLM, which they do KV caching, but they're not agentic oriented. They clearly mentioned that compared to vLLM, which is state of the art, they got the GPU utilization 87% compared to 70%. So 70% increase here, which is considerable. I told you about they got 2 times more throughput compared to vLLM, especially for peak load. And also the critical path got 75% reduced in abnormal agent, which is amazing. And in general, they had 47 latency reduction. So that means your agents can be 2 times faster with just simply having TokenCake on the top of inferencing framework that you use, let's say vLLM. Now in regards to implementation, what they added in their paper, what they do that they mentioned TokenCake has a front-end API to start to create a DAG out of your agent to understand what is a critical agent and all those space and time scheduler that we discussed. So to give you a pseudocode example, you need to specify this DAG of your agentic solution by yourself. Let's say you have a RAG agent. So you first create a graph and you have a node agent that is a planner agent. Then you have another agent that do RAG, which is retrieving information from your documents. And you have some sub steps within that node, which is query, taking the embeddings through search, and then generate that document or whatever you have through the RAG. So these are 3 sub steps on the RAG node. And then you give an estimation of how long that function call will take time. This is the part that I told you need to provide your estimation. Let's say gonna take 1.5 seconds or millisecond, whatever. And then DAG is just sort of a graph that has nodes and edges. Nodes are your AI agents, and edges can be connection to the function calls and tools or some other sub agents. They mentioned that they implemented this solution in almost around 9K lines of Python code. They created a custom kernel on GPU for having that offload from GPU to CPU in an efficient way. And they extended vLLM KV caching for just making it agent aware. And lastly, to have a quick comparison of TokenCake with some other inferencing LLMs from features standpoint, you can see that TokenCake is the only one that is function call aware for hosting language models. Compared to vLLM, Mooncake, Cache, Attention, these are different type of inferencing frameworks. And to the best of my knowledge, I haven't seen any other inferencing framework that consider your agent or function call for doing inferencing. Offload strategy, vLLM stuff, they don't have actually any offloading. If you want to transfer from GPU to CPU or other tiers like network disk, you have to utilize some other frameworks, let's say LM cache stuff, but it comes by TokenCake automatically. And prefetch strategy, that means when I want to get those KV cache back again to the GPU memory, how would I do it? TokenCake will predict by itself when to do so, but others, they don't have actually such a thing, or they're just pretty static. Now for agent priority, again, this is the only one that has a hybrid approach, understanding agent criticals, but vLLM is just first come, first serve. The other ones are not even considering your agentic use case. And memory partition, as I discussed, for having dedicated usage of memory for critical path versus non-critical or shared pool, they have a dynamic approach as we discussed, but the rest are just pretty static. Alright, that was all about TokenCake. Still, it's in the research phase, and they mentioned that they have tested the solution on just one single GPU, so there is a chance to improve the solution for distributed execution of multiple GPUs across multiple nodes as they become much more complex. But I truly see as a great potential to further improve the efficiency of inferencing these AI agents, given that they're getting much more complex. Number of agents, language models, and tools being used is significantly getting much more higher rate. So understanding all those contexts and then doing inferencing is certainly needed, just instead of naively hosting a language model and call it as an API for creating AI agents. I hope you found this video helpful. If yes, I would be very thankful if you click on like video, and make sure you share your thoughts or questions in the comment section below. And I added the link of the source paper to the video description below. There's a Discord channel link. Go to the Discord channel, and on the reference section you will see the link to all videos that I have created so far. And make sure you subscribe so you won't miss the next video. Thank you so much.